Assalamualaikum and good day everyone. So welcome back to my class on system identification. In the previous video, I have actually explained to you the derivation of least squared and generalized least squared algorithm. And for this video, I'm going to show you how generalized least squared is being used as an extended version of least squared to further update least squared estimation for unknown system, for parameter estimation of an unknown system. Let's have these particular problems. Okay, how to solve this particular problem? Let's say I have a system described by this equation where I have input to the system is actually u, and the transfer function of the system is a polynomial b over a. Okay, it is an arcs model with, let's say, model order 1. Okay, and the output here is x. Okay, and that x is actually correlated with noise. When I do this data collection, for example, I have some problem with the data collections, I have noises correlated with it. Okay, and that will be giving me my output. So that noise is actually a white noise. However, when we do the modeling, you will see later on that that white noise will become colored noise. Okay, in this case, yk is equals to b over a uk, okay, that is your x, okay, plus zeta. All right, okay, so when we have that, we can then further put the value of our transfer function b over a. It is actually, let's say, it is bz minus 1 from the problem that we have in the slide. B z minus 1 plus a z minus 1 multiplied by your uk plus your noise. Okay, then when I expand this equation further by multiplying yk with 1 plus z minus 1 to remove the denominator of this equation, you can see that the noise zeta is also will be multiplied with my 1 plus a z minus 1. Okay, so what happened is that my yk, if I multiply with that, so it's going to give me yk plus y plus a y k minus 1. Why is it so? Because when you have yk, you multiply with z minus 1, it will become a delayed data by 1. Okay, so that's why we get yk minus 1. Similarly, for the other side, you're going to have b u k minus 1. Why? Because when you have uk multiply with z minus 1, it will give you a delayed data. All right, and then plus your zeta, and this zeta will be multiplied with your transfer function a, which is 1 plus a z minus 1. I'm not going to expand that. I'm just going to show you that now this noise is no longer white noise. This noise is now becoming a colored noise, which is undesirable. Okay, so if I further rewrite this equation, yk is equals to negative a y k minus 1 plus b u k minus 1 plus that zeta multiply with the 1 plus a z minus 1. Okay, so now the idea is that I do not like this white noise to be multiplied with any transfer function. Why is it so? Because it will become a very huge error to my parameter estimation. So what I'm going to do is I'm going to remove that noise. Okay, how to do that? Okay, because I do not have my parameter estimation yet. So in the beginning, the first part, I will do simple least squared to estimate my parameters. So then afterwards, I will actually try to remove the parameter, remove the error by using generalized least squared. So let's say in the beginning, let's use simple least squared, okay, to have my system model in this form, and then we're going to use, I'm just gonna model, of course I'm going to model using y and u. Okay, I'm not going to use my noise because I do not know what is the noise, but I know it is correlated in my data. Okay, so if we form in a matrix form of y is equals to phi beta plus e is the error. Okay, and then we form the matrices of y and phi from the previous class. You can see from the previous least squared estimation. So I'm going to write this equation into a form of y k is equals to negative a y k minus 1 plus b u k minus 1 plus, I'm just going to call that error, isn't it? Because I'm not going to estimate that. Okay, so I'm going to ignore that part. So I'm just going to find out what is my a and b. This is using least squared. Okay, first. All right. So for the data, I know that I don't have that. I cannot keep it as k minus 1. Okay, here, and uk minus 1 here. Why? Because when I use k equals to 1, that will give me 0, isn't it? I don't have data 0, so I am going to shift that by 1. So by shifting by 1, I will have y k plus 1 is equals to negative a y k minus b u k, all right, plus my error, all right. Okay, so when I have that, I can then just put, if I put my k equals to 1, that is going to give me y2 when my k is equals to 2, this is going to give me y3 okay, and when my k is equals to 3, this is going to give me y4 sorry, this is u3 y3 and this is u3. So this is similar than the example of least squared that we have seen in the previous video. Okay, so I'm going to assume this, I'm going to put this in a matrix form, okay, where I'm going to have this as my y2, y3 and y4, and then I'm going to introduce to you the phi matrix where I have in here negative y1 and u1, negative y2 and u2, negative y3 and u3, okay, and then I know that this is going to be multiplied with my parameter of a1 and b1. I'm going to call that y matrix, and this is, I'm going to call it phi matrix, and this is, I'm going to call it beta matrix. Okay, so using this y equals to phi multiplied by beta matrix form, I know that somewhere here I will have the plus error, isn't it? Okay, all the way. So this one also plus error, isn't it? But I'm going to ignore the error part. Okay, so when we have this, when we can then utilize our beta is equals to phi transpose phi inverse multiplied by phi transpose y. Okay, we can utilize that formula to get the value of my estimated A. Okay, so you can see from the slide, I have put the value of my Y matrix, phi matrix, and also my beta. Okay, so I put the values and it's giving me the one that you've seen in the slide. So when we conduct the least squared estimation, when we calculate the phi transpose phi, it will give this matrix that you've seen here. Okay, this is phi transpose phi, and then this is phi transpose phi, then you inverse it. Okay, and then this is phi transpose y, and then the overall for your beta is your phi transpose phi multiplied by inverse multiplied by phi transpose y. So that will give me 0.56 for my A1 and 8.72 for my B1 or A and B. Okay, so we know that this data is correlated with noise, because you remember just now this y is actually plus some error at the end of it, isn't it? So this data is correlated with noise. So what we can do, we can then later try to postulate a filter to filter the data so that the noise can be removed. So how to do that? Okay, so I'm going to postulate a data. Now that I have my beta using this estimation, I already have my beta. The value of A and B is already being predicted. So the value of A and B as shown in the previous slide. Okay, it is equals to 0.56 and 8.72. Okay, so what I'm going to do now, I'm going to postulate the filter, and I will filter my input and output of my system. So this is done using least squared. Now I'm going to do generalized least squared utilizing the parameter that we estimated. Mind you, when you want to do generalized least squared, you have to do the least squared first, okay? Because you need the estimated parameter for forming your filter. Okay, so what is it that you want to filter just now? If you remember correctly, okay, if you look at the system, what you want to filter is this part, isn't it? Okay, that is what you want to filter out, isn't it? So 1 plus az minus 1. So let's design a filter. Okay, let's call that fz minus 1, and let's call that filter as 1 over a. Why is it so? If I have 1 over a, which is 1 over 1 plus az minus 1, if that is my filter, then my noise will be cancelled out. Okay, the parameter of my noise in this previous problem here, it will be cancelled out, so that noise will become immediately become just white noise. Okay, but how to filter that? So if you look at the equation again just now, if you remember just now, the equation was yk, okay, is yk equals to minus a yk minus 1 plus b uk minus 1, okay, plus your zeta multiply with that 1 plus az minus 1. Okay, so when I want to design a filter, I need to filter all of them. I cannot just filter one of them, isn't it? Okay, now hang on. Before I use that, it's better for me to use the initial equation rather than this equation. Okay, so the initial equation that I'm going to use is describing this system here. Okay, so this is better, isn't it? Okay, let's do that. Okay, so if you look at that equation, y is equals to b over a multiplied by u plus your zeta. Okay, when you expand that, just now it become ay is equals to bu plus a zeta. And then you do not like that a, isn't it? You want to filter it out. Okay, so then you're going to design a filter called f. So that f is f multiply with all the parameter, all the element that you have in your equation. Right? Okay, so of course the filter f cannot be multiplied with transfer function a in this form here, isn't it? Why? Because I need to keep that. I want to estimate my parameter. So instead of multiplying f in for this part, instead of multiplying f with a, I'm going to multiply f with y. Okay, so I'm going to have a fy equals to b. Similarly for b, I don't want to eliminate parameter b because I need to know what is my parameter, isn't it? Because I need to estimate my parameter. Okay, so I'm going to filter u, the data input of my system. Okay, in this case, f and a at this moment will be cancelled out. All right, because why? Because the filter is designed so that f is equals to 1 over a. Therefore, it can actually cancel the parameter a at my noise, right? So it will become white noise again. All right, now how do we filter y? So if I call that y filtered, okay, and u filtered, okay, plus zeta, this is what I want. Okay, then if I equate that equation, y filtered is simply equal, so let me just put k in that. Y filtered k is simply equivalent to f multiplied by yk. Alright, so what is f? F is 1 over 1 plus az minus 1 multiplied by yk. Alright, and then if I cross multiply that, it becomes yfk plus a yf k minus 1 is equals to yk. Okay, so if I can further rewrite that, I just want to have my yf k the filtered data, it is equals to the actual data, yk, okay, the data that you already have in the table just now, minus the AF, the previous filtered data. So the new filtered data will be equals to the actual data minus the previous filtered data multiplied by your transfer function A. Of course, this transfer function A, sorry, the parameter A, you do not have that parameter, you have estimated it, isn't it? You don't have the actual parameter, but you have estimated it from the previous least square example. Okay, I'm going to do the same thing for this one. I'm going to do the same thing for my input. Okay, so I'm going to do the same thing for input. So it's also going to give me the similar equation. So for input U filtered K, it is equals to U, actual U, okay, multiplied, sorry, the filter multiplied by your actual U. Okay, so U filtered K is equals to F is 1 over 1 plus AZ minus 1. Mind you, when you design the filter, it is 1 over 1 plus AZ minus 1. Then that is also the filter that you're going to use for U. You're not going to use BZ minus 1 for your U, okay? So it depends on your filter, not for your transfer function just now. Okay, so if I cross multiply these, I will have UFK multiplied by 1 is becoming what? UFK. And then for the UFK multiplied by AZ minus 1, it will give me AUFK minus 1. Okay, is equivalent to UK multiplied by 1. Correct? So then if I bring that part of my filter data to the other side, it becomes negative AUFK minus 1 plus UK, or I can further rewrite this in form of the filtered data is equals to the actual data UK, okay, minus the estimated A, okay, from your least square multiplied by the previous filtered data, the one previous filtered data. So that's how you do it. Okay, so let's put all the values into the filtered data. Okay, you will see later on, I put the value in the previous filtered data. So this is how it is. So if I put my F here, okay, my filtered data here, okay. So since for this problem, Y filtered 0 is already given, which is 29.97. So I'm just going to use that value for the first one when K equals to 1. So it's actually simply you take when K equals to 1, your Y filtered K plus K become K. Of course, you have to start with K equals to 1, right? So if you start with K equals to 1, in this case, Y1, Y filtered 1 is equals to Y actual Y1 minus A filtered, sorry, estimated A with Y filtered 0. Okay, in this case you have Y filtered 0. For the problem is given Y filtered 0 is 29.97. So you can just put that in your equation. All right, so if I put the value for Y1, Y filtered 1, it's equals to minus 16, which is from my tabulation of data. If you look at the data again, all right, okay, that's the data. So Y1 is negative 16. Okay, so put that negative 16 there. Minus your estimated A is 0.56 just now, isn't it? When you use least square, isn't it? Okay, multiply with your given filtered data. You're given from the problem, the YF0 is 29.97. Okay, so you're going to put that value there. All right. Okay, then you're gonna get this is equivalent to because I have actually calculate this. Okay, so I can just simply refer to the slide. It gives us a value of minus 32.78, minus 32.78. Okay, so that is what you're gonna get for the first Y filter. What about the rest of it? So you can straight away put the value of Y2. Y filter 2 is gonna be equals to put the value of y2. So in this case, y2 is 0 minus 0.56 multiplied by, okay, in this case, you need the value of y filtered 1. Okay, but because you have calculated the y filtered 1 earlier, that's the value that you want to use. So you're going to put it there. Okay, minus 32.78. Okay, and this is equivalent to, is giving us 18.356. Okay, then you're going to continue this utilizing this value to for the next filtered calculation. So for y filtered 3, it's equals to, you're going to put y3, which is in from the table is 9 minus 0.56, and then you're going to put that value here. Okay, 18.356. Okay, that is your y filtered 2, the previous data before. Okay, so that's going to give you minus 1.279. Okay, then lastly, you're going to use for y filtered 4, it equals to, you look at your table, what is y4? So y4 was 3, okay, minus 0.56, this is the estimated A, multiplied by that previous data, you're going to put here, minus 1.279. Okay, that's going to give us 3.7166. I'm going to do the same, okay, the same thing with my U filtered. So if you look at the slide here, I've done it for U filtered. I need to have U filtered 1, but since it's given U filtered 0, for U filtered 1, I need to have U filtered 0, and since it's given, then it's going to be used here. Okay, then I'm gonna calculate similarly for my y to obtain all this value for my U filtered. So this is the filtered input and filtered output data. Okay, so what's next? Put that filtered input and output that you have calculated into this table. So you can see that the table is actually having all the filtered value now, isn't it? Okay, so having to have that all the filtered value tabulated here, then you can use this data again for your least square estimation. So but now this is actually the second second iteration of least square estimation. So I'm not going to call that y, I'm going to call that yf, simply because the data that I use is the filtered data. Okay, so yf is equals to yf2, okay, which is 18.356, yf3 and yf4, and this is negative yf1, negative yf2, negative yf3. This is u1, u2 and u3. Okay, so in my filtered phi, okay, phi filter. Okay, so then put that back in the least square estimation, phi transpose phi, but instead of using phi, we're going to use phi filtered phi here. Okay, so similarly for phi transpose y, you're not going to use the actual phi, then you're going to use the filtered phi and the filtered y. So this is the value that you're going to get. And then lastly, when you multiply both of them, okay, you're going to get your estimated parameter b, which is 0.54 and 8.5. You see that these value have improved from the previous value. How do I know it's improved? You can know by calculating the error of the system, and then from the predicted output, you calculate the error, and then you get to know that these value are much better than the previous estimation. So what to do next? Using this is your second time predicted A, isn't it? A predicted A, isn't it? This is the second time predicted B. You can then use this predicted A again, okay? Use that predicted A again to estimate your, to calculate your filter A and filter output and filter input, and then use that filtered output and filter input to calculate your beta again. So this is the iteration that you need to repeat, okay, over and over again until the error become minimum. All right, so I think that is all for this example. So maybe one question that arises is that how can we get this filtered input in the beginning, the y filtered 0, isn't it? Okay, how do you get that in the beginning? Okay, when we don't have y filter 0, we can use the actual data. So in this case, if you don't have y0, you're gonna start by shifting this value. You cannot find the first value, you're gonna use the second value by shifting it by 1. Okay, so then y filtered value, or y filtered 1 here is going to be your actual data y1. It's not y filtered 1. So how do I get that value? Because I generate this data, so I can actually filter the first, maybe I generate the data by 1000 maybe, so I can filter the first 900 data, okay, and use that as my initial filtered value. Okay, so when I have filtered it more and more, so it become a so-called clean data, a filtered data. Okay, we can use that as our starting point. All right, then I can just use this. Actually, instead of 1, I can use the 900 datas, okay, onwards. All right, after I have my filter. But anyway, I will show you more example in the next class. Okay, so if you have any question, you can contact me and ask about the assignment. I already give you the I'm going to give you the assignment through our group, okay, and then you can ask me anything related to that assignment. Okay, thank you so much for listening.